Welcome to the lesson on section 5.5, the substitution rule. In this lesson, you'll learn about integration by substitution, which will allow us to integrate expressions that would have been the result of finding a derivative using the chain rule. Before we start the examples, let's look at the steps involved in the procedure. In order to integrate by substitution, we'll need our integrand to look like an inner function plugged into an outer function times the derivative of that inner function, just like the result of the chain rule. First, substitute a variable in place of the inner function. We typically use the letter u here, and substitute a du in place of the derivative of the inner function and the dx. Integrate in terms of u, and then substitute the x's back into the result. In our first example, we'll integrate sine of x over cosine to the fifth of x. Look for the more complicated part of the expression to identify your inner and outer function. The denominator can be thought of as the fifth power function with cosine of x plugged into it. We let u equal the inner function cosine of x. Taking the derivative of both sides of u equals cosine of x, we get du dx equals negative sine x. And multiplying both sides by dx gives us du equals negative sine x dx. We don't exactly have negative sine x dx in our integrand. We have positive sine x dx instead. To make a match, I multiply both sides of this by negative 1. This means that we'll be replacing the sine of x dx with a negative 1 du. To substitute, replace the cosine of x with u and sine x dx with negative du. To integrate, I would rewrite the u in the denominator as u to the negative fifth power, so I can use the power rule. Applying the power rule for integration, increase the exponent by 1 and then divide by that exponent. To finish, substitute cosine of x back in place of the u. So the integral of sine of x over cosine to the fifth of x dx is 1 over 4 cosine to the fourth x plus c. Our next example is a definite integral. I'll show you two different ways to deal with the limits of integration. I can see the function sine of x plus 1 plugged into a cubing function. So we'll let u equal sine of x plus 1. Taking the derivative of both sides, du equals cosine of x dx, which is an exact match to part of the integrand. When I substitute u in place of sine of x plus 1, it won't make sense to leave the limits of integration the way they are, because the 0 and pi over 2 are x values. To convert to u values, use the fact that u equals sine of x plus 1. Plugging in x equals 0, I find that u equals sine of 0 plus 1, which is 1. Plugging in x equals pi over 2, I find that u equals sine of pi over 2 plus 1, or 2. That makes my new problem the integral from u equals 1 to u equals 2 of u to the third du. And note here that these numbers go back in place of the x's that they came from. So if for some reason the larger number ended up replacing the lower limit of integration, you would still go that way. You wouldn't always just place the lower number on the bottom and the higher number on the top. So then integrating, I get u to the fourth over 4, and I have to evaluate that at 2 and 1, and then we get 15 over 4. In method 2, I'll still use u equals sine of x plus 1 and du equals cosine of x dx. But this time, I'll omit the limits of integration until after I integrate. So we still get u to the fourth over 4 after integrating. But this time, I'll substitute sine of x plus 1 back in place of the u before evaluating at the original limits of integration. Plugging in pi over 2 and 0 for x, and we'll still get 15 over 4. So whether you use method 1 or method 2 will be up to you. I'm more likely to use method 1 most of the time, so I'll be converting the limits of integration to u values and then continuing the rest of the problem with u's up to the end. Let's look at a few more examples and decide how we would substitute. I won't complete the integration for most of these, but you're welcome to do so for practice. The first one consists of the function x plus 1 over x minus 1 plugged into the cosine function. So I would let u equal x plus 1 over x minus 1. Taking the derivative of both sides, I have to use the quotient rule, and you'll get that du equals negative 2 over x minus 1 squared dx. I don't have an exact match to what's in the problem, but I can make it match by dividing both sides of this equation by negative 2. That means that I can substitute negative 1/2 du in place of the 1 over x minus 1 squared dx that is in the integrand. Performing these substitutions gives me the integral of cosine of u times negative 1/2 du. And then integrating, I get negative 1/2 sine of u plus c. And substituting the x's back into the problem, we have negative 1/2 sine of x plus 1 over x minus 1 plus c. In this one, I can see the function square root of x plus 7 plugged into the 8th power function. So I'll let u equal square root of x plus 7, and du equals 1/2 x to the negative 1/2 dx, which is really 1 over 2 square root of x dx. Again, I don't have an exact match to the rest of the integrand, but I can multiply both sides of this equation by 2 to get a match. After substituting, I would get the integral of u to the 8th times 2 du, and then we would integrate from there. In this one, there's a sine function plugged into another sine function. So let u equal sine of x, then du would be cosine of x dx, and substituting gives us the integral of sine u du. Here we have the function cosine of x plus 2 plugged into a cosine function. If we let u equal cosine of x plus 2, then du is negative sine x dx. Multiply both sides of this by negative 1 to make an exact match to the other part of the integrand. And then substituting would give me integral of cosine u times negative 1 du. And in my last example, there is a secant function plugged into a power function. If I let u equal secant of x, then du is its derivative, secant x tan x dx. In order to make a match for du, I need to do some separating in the integrand. So I need to think of it as secant squared times secant x tan x dx. And then substituting would give me the integral of u squared du. This concludes our lesson on section 5.5, Integration by Substitution.